Welcome everyone. Welcome to the series of computer architecture. It is a continuous series. We have already seen about the basic computer architecture, followed by arithmetic operations, and followed by practical problems involved in developing and solving Booth multiplication algorithms. And with the continuation of that, we are going to see pipeline and hazards. So in this session, we are going to see about the basics of pipelining and how hazards occur in pipelining and how we can able to rectify those hazards to enhance our performance. Okay, so coming to the session, here with you I am presenting the pipeline hazard presented by myself, Narendran, from IT department. Okay, so pipelining. Pipelining is a basic word we can see everywhere in computer architecture subject. So what is pipelining? So pipelining is nothing but every instructions to be executed in a proper manner, and also these instructions that we are going to execute will be channelized in a proper way so that the performance and throughput will be increased. How we can see in this particular session. Okay, so pipelining is widely used in modern processes. So because it basically involves instruction execution and how we are going to provide those instructions in a proper way. So pipelining improves the system performance, and in terms it increases the throughput. Okay, so pipeline organization requires sophisticated complication techniques. Okay, it can be with sophisticated techniques, and it can be implemented with basic techniques also. Okay, that we will discuss in the coming session. Okay, so we'll just see the basic concepts involved in a proper execution of pipelining. So first of all, we should see how we can make the execution and make the programmers to execute the instructions faster. Use faster circuit technology to build the processor, that is CPU, and the main memory. So we have to arrange the hardware so that more than one operation can be performed at a same time at a particular period of time. Simultaneously, number of instructions can be executed at a particular period of time. Okay, in 1 second, if we can able to execute more number of instructions, then we can say it as a pipelining. In other words, we can say pipeline basically improves the multi-programming and multitasking. Okay, the number of operations performed per second is increased, even though the lapsed time need to be performed. That is not going to be changed. Okay, so traditional pipelining concept. Okay, so everything that we move linearly is a traditional pipelining concept. For example, in the screen you can see A followed by B followed by C and followed by D. So when the particular set of instructions or particular set of things are given one by one serially, one after the another, then there will be a process of linearity that prevails in the proper execution, but the time taken for it to complete the whole task will be a question mark. So because everything when we move in a linear fashion, that is we move in a serial way, then there will be a possibility of consumption of more number of time. Okay, we can discuss with this example. For example, if A, okay, so there are four instructions, A, B, C and D. Okay, so these four instructions are to be completed sequentially, means, okay, first in the first um, A is going to initiate. It starts with the 6 p.m. and it ends in 7 p.m. So next, after this execution process gets over, the next process starts, that is the process B, task B starts at 8 a.m. and it winds up at 9 a.m. Next, followed by B, after the B fully completes, C start executing and it is uh, providing the execution part. So after the C part, C task is executing, next the D instruction will be executed. When these kind of instructions, that is sequential flow of instructions, are carried out in any kind of processors, then the processor has to wait for a longer period of time to complete a particular task. So it's a greater time consumption process. So the pipeline task, okay, has differentiated this into a particular way so that the proper execution can be completed in a prescribed period of time. For example, the same task that we have already seen is differentiated, that is the when A instruction is going to start and it is going to execute, it is in the final state, for example approximately 7 p.m. So at the end of the execution of A instruction, the B instruction gets started. So it does not wait for the A instruction should complete its task fully. So whenever the previous instruction is going to execute, the next instruction will be initiated. So this is a traditional pipeline, a quite altered way. Okay, it can able to execute instructions and provide throughput much faster than the older one. So time will be saved by using this type of instruction. So in other words, we can say pipeline does not help latency of single task. It helps throughout the throughput of entire workload. So pipeline rate limited by slowest pipeline stage. Also, multiple tasks operating simultaneously using different resources. So pipeline speed up is, we can equate it with the number of pipeline stages. Normally, in an unbalanced length of pipeline stages will reduce the speed up process. A time to fill the pipeline and time to drain it reduces the speed up. So stalls for dependency. Stall we can discuss in the later sessions. Okay, so this is the basic sequence of pipelining. So it involves 4 different tasks. One is fetch, execute, store. These kind of tasks will be carried out throughout the particular period of time. So normally we can say that pipelining is defined as 4 different stages. For example, fetch, decode, execute and store, or we can say it as write operation. Okay, so I am zooming this. So here we can say that a pipeline buffer will be having fetch of instruction. The fetching of instruction will be sent to the buffer 1 and the output will be given to the decode instruction. Here the operands and operators are decoded and the output will be given to the buffer 2, and after processing it will be executed, and finally the output of the particular execution will be written as a result. Okay, so this is the basic hardware organization of a particular pipelining sequence. Okay, so here there is a important role for cache memory. So each pipeline stage is expected to complete in one clock cycle period. Okay, when this clock cycle gets increased, the throughput will be a question mark. So the clock period should be long enough to let the slowest pipeline stage to complete faster. The faster the stages can be, only wait for the slowest one to complete first. Okay, So in order to process this, we are in hand, we are having a cache memory. The potential increase in performance will be carried out by means of cache memory. Okay, it will temporarily stores every recent instructions that are to be executed. Suppose when there is a need for result of a particular instruction, we can get it from the last updated cache memory. So this will reduce the time to search for a particular content. Okay, so this is the basic pipelining. So when the execution operation takes more than one clock cycle, the effect will be like this only. As you see in this particular diagram, in the first instruction I1, fetch, decode, execute and store F1, D1, E1 and W1 is doing in a proper manner. In the second instruction, before the decode operation begins, the second instruction starts fetching the particular instruction set. So the execution phase gets longer. As the execution phase gets longer for instruction 2, it will be reflected in instruction 3 and instruction 4 followed by instruction 5. Ultimately, we have to reduce the number of clock cycles taken for completing a particular instruction in a prescribed period of time, right? So this will be the effect of execution of operation taking more than one clock cycle. So in such cases, the pipeline may be stalled for a particular period of time. For example, here you can say the pipeline is stalling for 2 clock cycles. Okay, here. So in such cases, the happening of hazard will occur. Any condition that causes a pipeline to stall for a particular period of time, whether it is a short period or whether it is a infinite number of time, it gets stalled means it is considered as hazard. So hazard is a brief topic. We are just getting into this. So there are many different types of hazards occurs. So we can differentiate it into basic 3 types of hazards. First one is data hazard. Okay, the data hazard is any condition in which either the source or the designation operand of an instruction are not available at the time of execution of a pipeline. So such kind of operation is considered as data hazard. Suppose the instruction is needed for performing a particular operation, but we can't able to find out the source data or designation data operand. So in such cases, there will be a delay in pipelining. The delay in pipelining will lead to the process called as hazard. It does not only affect the one stage of pipeline instruction, it affects the whole pipeline stages. So next one is instruction hazard. So it is otherwise called as control hazard. Why it is called as control hazard means the instructions we are going to process will be based upon the control instructions. We are very familiar with the basic control instructions, right? So some of the basic control instructions are write, read, write, protect. So these kind of instructions are there. So suppose when there is a delay in availability of these kind of instructions, this may cause the pipeline to stall. Okay, so this kind of stalling operation when occurs in the pipeline due to the unavailability or unavailability of instructions, that is control instructions, means it is considered as instruction level hazard or control hazard. The next one is structural hazard. The situation arises when 2 instructions require the use of same given hardware resource at the same period of time. Suppose we are having 2 printers, the 2 printers have to be accessed at a particular same time, then there will be a situation called as structural hazard arises. So in such situations, we are considering it as structural hazard. So these 3 different types of hazards are paying way for basic pipeline performance discrepancies. So whenever we are planning for pipeline performance increase, we have to look into the precautionary steps so that data hazards, instruction hazard or control hazard and structural hazard should not occur in a basic pipeline operations. Okay. So pipeline performance. So we can also say that pipeline performance is decided by number of stalls occurred in the particular pipeline sequence. Suppose for example here you are having I1, I2, I3, three types of instructions. So when these instructions are fine tuned in a proper way, then it can be executed within 5 to 6 clock cycle period. But here you can see that this in three types of instructions are holding 9 clock cycle period. So where it gets distracted means here the fetching operation gets stalled for a period of time. So when this second instruction gets stalled, the same will be reflected in the upcoming next instructions also. This will be monitored by program counter. We have already discussed the program counter. The program counter is nothing but it can able to process the next instruction to be executed. So when there is a condition called stalling occurs, it will be happening for idle conditions in subsequent instruction sets. Okay, so such kind of tactics should be um, affecting the pipeline performance. Okay, so basically what we have to see is we have to ensure that pipeline performance should be increased. Okay. Okay, now we can able to move on to the part called data hazards. Okay, so data hazard, we have already seen that when there is a unavailability of data at a particular period of time during the proper execution of instruction, so then the pipeline will be stalled. So in such cases we can consider it as data hazard. So consider this example: a tends to 3 plus a and b tends to 4 into a. So in order to execute B instruction, the A instruction should be properly executed first. Then only we can able to process. For example, here A tends to 5 into C and B tends to 20 plus C. Okay, when two operands depend on each other, there must be a sequential execution in proper order. Okay, so here is the example for what we have seen in the last slide. Okay. So operand forwarding. Operand forwarding is one of the important technique used to prevent and used to avoid the data hazards. Okay, a special arrangement needed to be made for forwarding the arithmetic logic unit output as the input to the ALU. Okay, so this is what operand forwarding will do. I will zoom it. We'll just have a look at it. So here source 1 and source 2 are the two operands. So they are getting executed and we are getting the result. Over the period of operation it gets executed. Suppose when there is a data path error occurs, then we have to forward this operand from the result part to execution part. It will be looped over a particular period of time until the execution will be successfully completed. So then we can move on to the execution part. So the execution part completion will lead to the writing or storing of a particular data into a particular register file. So we can say that operand forwarding is the best technique to handle data hazard. Okay. So though there are some of the important aspects involved in operand forwarding techniques, there will be a set of side effects too. Sometimes an instruction changes the content of the register other than the one that is to be designated. So these kind of overwriting operations can be done. There is a possibility for these kind of things occur when we deal with operand forwarding technique or any other technique which helps to convert this hazard into a normal operation. Okay, so that is one of the important technique. Okay, so next one is instruction hazard. So instruction hazard, whenever the stream of instructions are to be fetched, if they are interrupted, then it will lead to a operation called as a stalling operation or bubble. So catch, miss and branch prediction are one of the important conditions that we deal with removing these instruction hazards. So branch timing also decides these kind of instruction hazard to be converted into an execution. successful execution. Okay, so delayed branch. So suppose when there is when there is a possibility of hazard occurs, we can able to delay a particular set of branch instructions so that the previous instruction will be executed fully and we can move on to the next instruction. Okay, so branch prediction, to predict whenever and wherever whether or not a particular branch will be taken or not. So assume when there is a branch and the branch will not take place and continue to fetch instructions in a sequential address order. So until the branch is evaluated, the instruction execution along with the previously predicted path must be done on a speculative basis. Okay, so that is the instructions are executed before the process is certainly going to be executed correctly. Okay, so these kind of instructions are very essential. So branch prediction plays a very important role in this kind of instruction hazard. Okay, so so in this session, we have dealt with the basic different types of hazards. Okay, so so just we have a quick look into what we have seen. Um, so we have seen about the basics of pipelining, followed by how the proper pipeline can be channelized, and how the pipeline idea should be done, and what is the role of cache memory in this pipelining, and how can we able to improve the performance of pipelining. So followed by different types of hazards: data hazard, instruction hazard, that is control hazard, and structural hazard. So in this data hazard, we have look forwarded into operand forwarding technique, and how we can able to handle this data hazard and what are the side effects. Followed by instruction hazard, how the branch prediction and cache properties are helpful in dealing with these kind of um, instruction hazard. Okay, so with this we can wind up this session. We can see about the different types of structural hazard in the upcoming um, session. Okay, so with that note, I am winding up this session. So in this in the next session, we can able to see the continuation of this pipelining concept. So until that, take care. Thank you.